Okay, I think now's a good time to start. And then, of course, people can still join. Let's start. So welcome everyone to this webinar where we will learn about PIC-based switch design and system level analysis. Um, Photonic Integrated Circuit switches play a crucial role when scaling in data centers and enabling fast and energy-efficient communication between the nodes. And integrating these subsystem modules in a single PIC improves the overall footprint in the space and reduces energy consumption, in addition to reducing cost. So characterizing the PICs in a chip level as well as in a system level is crucial for system designers. And typically the chip level design is followed up by system level integration and testing. So in this session, Luceda and Optiwave will demonstrate a complete workflow for PIC switch design and analysis. And we'll begin by designing a cross-connect switch layout using Luceda's IPKISS. And we'll explore how to model and analyze the PIC device non-idealities such as optical crosstalk and their impact on circuit performance. And then from there, we'll transition to the system level with Optiwave's OptiSystem software, embedding our design PIC in a black box model to simulate real-world performance. We'll investigate different modulation schemes, speeds, and test scenarios to give a comprehensive understanding of how PIC subsystems interact and how to mitigate potential design challenges. And by the end of this webinar, you'll see firsthand how to seamlessly integrate Luceda's IPKISS and Optiwave's OptiSystem. To do this, we have two great speakers today who will guide us through from the Luceda side and the Optiwave side. So first, from Luceda side, we have Nirav Adavarapu. Nirav is an application engineer at Luceda Photonics, and Nirav's background is in electronics, and from there he studied a master in nanoscience and engineering before undertaking his PhD in photonics. And Nirav now works to provide comprehensive technical support to Luceda's users. And from Optiwave, we have Dr. Ahmad Attia, with a PhD in electrical engineering from the University of Ottawa and extensive academic and industrial experience. His research interests lie in the field of optical fiber and free space optical communication systems. Over the years, he has authored more than 125 technical papers and holds over 30 patents, reflecting his deep expertise in optical fiber characterization, amplifiers, nonlinear optics, and transmission systems. And he currently serves as the Vice President at Optiwave Systems. The schedule for today, we have the welcome and introduction. And from there, we will switch over to Luceda Photonics, where Nirav will talk about the synthesis of the PIC chip analysis. And from there, we hand over to Optiwave Systems, where Ahmad will talk about the analysis of the switch in OptiSystem. And we have time at the end for questions and answers. If you have questions that come up during the presentation, please write them in the chat and we will address them at the end. Or alternatively, you can wait until the end and then, raise your hand and we will ask the questions live. Okay, and so with that, thank you everyone again, and I will now hand the floor to Nirav from Luceda.
Thanks, Craig. All right, I shall share my screen. There we go, and present. Yeah, all right, so welcome to this webinar on PIC-based switch design and system level analysis by Luceda and Optiwave. So just to give a quick introduction, as we all know, optical links facilitate ultra-high bandwidth communication because you have a high-frequency carrier wave and the ability to transmit multiple channels in the same medium, which is typically an optical fiber. When multiple endpoints use optical links, you need a switching network to coordinate an input channel to the correct output. A few application domains of optical switching networks are listed here. The most obvious one is telecommunications, where they can be used in mobile networks. But you can also use switching networks to coordinate data packets between different computing nodes in a data center, and even extend it to intra-chip communication. For example, AI models, which would need to be trained on massive data sets, could also benefit from a higher data transfer rate between computing cores. And using an optical switching network to facilitate the communication is quite beneficial for this. You can implement PIC-based switch-based programmable photonic circuits like the feed-forward mesh shown in this figure. And you can also apply switching circuits in quantum computers where they have been used to initialize the spin of a qubit and entangle two photons. And they have also been used for deep learning. They've also been used to implement deep learning networks using photonic solutions. Switching networks are usually based on cascading multiple unit cells, which are typically comprised of 2x2 switching blocks in different schemes to achieve n-cross-n routing. Individual switching action between different output ports is usually achieved by leveraging either the electro-optic or the thermo-optic effect in different ways. You need to optimize the bandwidth, minimize the insertion loss and crosstalk and so on for these unit switches. But once that's designed, you'll also have to place these 2x2 blocks in different schemes to achieve non-blocking switching across n-cross-n ports. So some of the architectures would be crossbar, Benesch, butterfly, Pylos, and so on. You'd want to evaluate all of these architectures with the same criteria, loss, power consumption, and so on. And you want to do a systematic comparison to make sure that the choice of the architecture and the 2x2 cells are evaluated rigorously. And this is what we'll be diving into a bit today. To implement a switch or any photonic integrated circuit for that matter, you can design it in Luceda's photonic design platform, where you would design your components from scratch or use a foundry guaranteed component from a PDK. Then you would create your circuit by placing components on a layout, specify connections, and perform simulations to check whether it behaves as you would expect. You would then perform design verifications to make sure that it behaves as you expect and finalize your design. And after that, you would perform PIC level analyses to evaluate the performance specs and compare it to different PIC implementations. On the other hand, you could also model your link in the OptiSystem environment, where you can leverage the tools to model the behavior of your transmitted light and include the effect of driver electronics, antennas, the different communication channels, and do a link-wide analysis. Today, we shall show you how you can design a switch in IPKISS and export it to OptiSystem to simulate how a switch would behave in a wider optical link. But before I dive into the technical content, I would like to give a quick introduction to Luceda and our product offering. Luceda Photonics was founded in 2014 out of the Belgian photonics ecosystem. It was created with the long-term goal of enabling photonics IC designers to enjoy the same first-time right design experience as electronic IC designers. Our mission is to accelerate the time to market of big design teams by helping them set up a flexible and efficient design flow. We have a presence around the world, including a branch office in Shanghai. We also have a partnership with Spark Photonics to best serve the photonics engineers in North America. We also have resellers in Taiwan and Tokyo. By using Luceda, you will have access to a team of photonics experts who will help you achieve your goals. The way we aim to achieve our goal is through the photonics design platform, which is a comprehensive Python-driven design platform that leverages the flexibility and automation of code to take you all the way from component design through circuit design and design validation. You can do parametric layout of your components and associate a numerical model to it to describe its interaction with your light. So this model could be informed either by data or a simulation or even a custom analytical model which you write. Once your component is designed, you can place them in a circuit and connect it up with other components and leverage our placement and routing engine to get a lot of flexibility in the design of your circuit. The layout is tightly linked to simulation, so changes you make to the layout would be reflected in the simulation without manual translation work to different platforms. We also have utilities to detect common design errors, such as acute angles or unintentional waveguide crossings. Since Luceda is based on Python, you can leverage one standard language for all aspects of your photonic design flow. These features help reduce your design errors and improve your time to market. So this slide shows the entirety of the product offerings of the Luceda Photonics design platform. It consists of our core product offering, which is IPKISS, and this includes features such as circuit and component layout, optical and electrical routing, and so on. You can simulate components using our built-in EME solver called Camphor and simulate the response of circuits using our circuit simulation engine Caffe. You can also visualize the schematic of your circuit using our GUI tool, IPKISS Canvas, and perform post-layout validation. Furthermore, we offer specialized tools to specialized modules such as Luceda AWG Designer to help you design arrayed waveguide grading circuits from a specification point of view, and Luceda IP Manager to help you manage your photonic design IP. We offer integration with a few third-party softwares like ANSYS Lumerical, Dassault Systems, and Tidy3D to help you perform FDTD simulations on your components. And we also have a link with Siemens EDA or to export your P cells to Tanner tools, and a link to a DRC checking tool on the Tower Semi process at the moment. Finally, we have a new link with OptiSystem to do system level simulations, which we shall demonstrate today. We offer process design kits across many different platforms from different foundries. We also offer design kits for assembly and testing to make your PIC packaging and testing process smoother. And finally, included in the software license, we also provide dedicated training and support to our customers. This includes Kickstart training sessions tailored to your needs and extended customer support to help you use our product to create your designs. On Luceda Academy, you can find extensive training material and documentation online. All right, so let's dive into the topic of this webinar, which is switch design. As I mentioned at the start of this presentation, you can have different switch architectures and you want to evaluate the properties such as insertion loss, crosstalk, and footprint rigorously. What you want from your design tool is the ability to adjust the layout of your circuit and do simulations with ease. So you want to be able to iterate over different designs easily and make changes to your layout. Ideally, with a parametric approach, you just have to punch in a few numbers and you'd get a circuit with as many inputs as you'd like with very little manual effort from a designer. Circuit simulation must be powerful, where you want to be absolutely sure that what is being simulated is what is drawn on the layout. And you also want to analyze all output spectra in the same way so that there's apples to apples comparisons between the different architectures. So these three aspects, design, simulation, and analysis, it's possible to do each of these steps individually in different softwares, which can get tedious, especially when you iterate over different designs. Debugging them can become very cumbersome if these tasks were distributed across different platforms. And we offer a solution where you can do virtually all three of these steps on our platform. From a bird's eye view of our platform, a user is given three axes of control. So there's layout, where you have control over components, connections, and placement, which is all defined in Python code. You can make a parametric circuit to freely change the circuit as you please, either the 2x2 switching block or the wider switching network. You can, any changes that you make to your layout would be reflected in the simulation. And it's possible to do both frequency domain and time domain simulations in IPKISS. You can apply any input signal you want and probe legitimate ports in your circuit. And the user is given control over what inputs he can apply and what ports he can probe without messing with the layout. Finally, you can plug your circuit into a test bench and evaluate its properties with no regard for what is inside. So there's no back and forth between softwares, and it's all seamless and done on one platform. Let's move to the first aspect, which is layout. There are two ways to approach circuit design. One is starting from a schematic of components which you'd like to place, and then write code around it. And the other is just to directly get started with writing Python code to draw your layout. We shall use the first approach. From a schematic point of view, a 2x2 MZI consists of directional couplers which are connected together using heated waveguides. IPKISS Canvas, which is a GUI tool, helps you define circuits and draw circuits and define connections between them. It can also export an initial version of the Python code to help you get started. Of course, you can always add optimizations and parametric functionality to this to make it more flexible. When you draw a circuit, when you draw the 2x2 switch in IPKISS, it should look something like the upper right image. So the pseudo code shown in the slide is very similar to the actual code you would use to define an MZI in IPKISS, but I removed some of the syntactical jargon to improve the clarity. So it's almost like writing English. You'd say place the first directional coupler at the origin, place a heater at a certain offset away from it, place the second directional coupler at a certain offset away from the first directional coupler, and connect these components using a Manhattan connection. So one of the outputs of the directional coupler is connected to a heater using a Manhattan route, which is basically routed at right angles. And this MZI can be reconfigured with different offsets, heater lengths, etc., by just changing one line of code or just the variable which is passed to this. The final circuit can be exported back to Canvas to visualize the circuit schematic with every element involved, including the connecting waveguide, which is shown as a lumped element in this schematic. I created a 4x4 circuit in the Benesch architecture by cascading 2x2 blocks. And I added in a waveguide crossing component with low insertion loss, reflection, and crosstalk. The creation of a 4x4 circuit is very similar to that of the unit 2x2 block, where I just tell IPKISS, place the first 2x2 block at the origin, place the second block at a certain offset away from it, connect it using a simple bent waveguide, and so on. The schematic capture tool allows you to visualize large functional circuit blocks without being overloaded with information about the implementation of every subcircuit. Here, you can see that the entire 2x2 block is just abstracted away in one block. And you can see how these 2x2 blocks are connected together to form a 4x4 Benesch circuit. And you're not bogged down with details of how it's implemented. Of course, the beauty of using IPKISS and parametric design is that the 2x2 block or the switching or the crossing can be replaced with ease in code, and this would be reflected in the circuit simulation as well. Speaking of which, let's talk about the circuit simulation aspect. So to simulate a circuit, what the only thing IPKISS needs are compact models for all of the components which are involved in the circuit. So, for example, you would need to know you need to have a behavioral model of how your directional coupler would behave. You need to have information on the refractive indices of your waveguide and knowledge of how the heater's index would change as a function of a certain current applied to this resistor. IPKISS would read the circuit model of every subcomponent and calculate the transmission across both the output ports. So for example, I ran a voltage sweep for this simple circuit from 0 to 4.5 volts to show how the transmission of the circuit changes as at a wavelength of 1550 nanometers as a function of voltage bias. And you can see that for two specific voltages, the signal is almost entirely transmitted in one of the two output ports, which I use to select the cross and bar bias voltages. And I also perform some basic analyses to show that, yes, the insertion loss is quite low in both of these configurations, and the crosstalk is also below minus 65 dB. What I should also point out is that I'm using components from our example PDK called SciFab, which is shipped with IPKISS. So it's not a real PDK. It's not a real PDK, but you can substitute it with components from a real PDK to see what how the performance would change. Now that we know what the cross and bar voltages are, let's see how we can apply it to a 4x4 Benesch circuit. Circuit simulation will account for local changes to the subcircuits based on the voltages which are applied to them. I show here an example where some of the switches are biased in the cross configuration and some of them are biased in the bar configuration. And you can trace the path, for example, of input number 1, which is on the lower left side, of how it propagates through the circuit. And the path is denoted using these red arrows. So you can see that input number 1 is expected to appear at output port number 3. And this is in fact exactly what we see even in the simulation. So the point is that Caffe can read the biases which you provide to the circuit, and for any arbitrary bias, it would be able to model how the signal would propagate. You can see that most of the power is transmitted to output port 3 here, and there's also a little bit of leakage into the other channels as well. All the inputs transmissions from the input ports arrive at the expected output ports of the circuit. The transmissions are almost equal, with some marginally lower transmissions for the other input channels owing to extra insertion losses. There's also ringing, which is observed in this circuit, which exists due to a weak resonance formed by the crosstalk introduced by the crossings. And as a matter of fact, if you replace the crossing with another equivalent with a much lower crosstalk, this ringing disappears. In this way, you can also perform analyses to see which components create an impact on the response of your circuit. Moving on to a circuit level analysis, we have IPKISS methods which can analyze the spectra which Café can simulate and extract common parameters which photonic designers would be interested in, such as insertion loss and crosstalk between different channels. Of course, since our platform is based on Python, you can also implement your own routines using Python. Yeah. Once you've finalized your analysis methods, you can implement a test bench in IPKISS, which evaluates all possible states of a given switch circuit. The analyses performed by this test bench would be independent of the implementation of the switch. So you can run all your standardized tests on a switch. For example, you can throw in a Benesch, Banyan, Crossbar, Pylos, or any switch architecture you want and do an apples to apples comparison between the performance specifications of different implementations. You can write the results to an output file. For example, I use a built-in function in i3.spectrum analyzer to analyze my circuit spectra and output them to a JSON file, but you can do your own analyses and output the data as you like using Python libraries. Once you finalize the parameters of your switch circuit architecture, you can export this PCell to OptiSystem, where you can simulate how the circuit would behave in the context of a wider optical link and evaluate the performance of your system. Ahmad from Optiwave shall now take you through the second half of the story.
Thanks, Nirav. Thanks, Greg, for the introduction. And let me share the screen here. Okay. And let me share presentation. And go into, okay. Okay, so again, it's just continuing on what Nirav was giving on the demonstration for this cross-connect switches. I'm gonna give some overview before on Optiwave and show you the product line, as well as discuss the black box component, which Greg was mentioning, which we call it Luceda simulation component, which you plug into it any PIC circuit, and then eventually analyze it in a system. Then we show you the demonstration of the 4x4 cross-connect switch in an OptiSystem layout and provide you with some feats on analysis. Okay, Optiwave established in 1994. It's over 30 years old company, and we are located in Ottawa, Ontario. We do software, and mainly our software tools be used for designing, simulating, and optimization for components, links, systems, and photonics optical communication networks. The software enables you to basically shorten the product line introduction into the market and improve the quality of your product eventually, and cost-effective enhancement as using the simulation before you making your product. And this webinar actually an example of the advantage which you could get from doing simulations ahead of manufacturing of your product. Optiwave software packages, we categorize them into 3 categories. One of them is the system level, which OptiSystem is one of the software packages we're going to talk about today. And there is another software called OptiSpice, which is an optoelectronics software. You can design optoelectronic circuits in the same layout and do simulation. The other software packages is a component level, which is like including finite difference time domain, which is OptiFDDT, as well as mode solvers, OptiMode, and beam propagation method, OptiBBM, and then 2 other software used for designing different types of fibers, single mode, multi-mode, and so on, as well as grading design, which you can design fiber bright grading, short length, long period gratings, tilted grading as well. The last software is the instrumentation software, which you would be able to connect your equipment regarding of the vendor of the equipment. All of this equipment, you can control them remotely using OptiSystem software, and then set up these equipments, collect data, and then process the data. Optiwave, this is some statistics about Optiwave, which shows you how like 30 plus years business in this field will performing. And then as you can see, also Optiwave is selling the product or licensing the product in different universities, research institutions, as well as governmental institutions. This is a snapshot of some of our customers in the industry, as well as in some universities. Now I'm going to tell you how to be able to download our software from Optiwave. You can website, so you can go into Optiwave website, and then once you go to download page, you click on it. You have the 30 days evaluation link, and that will take you to the registration page. You register username, you create username and password. Once that is created, you will be able to download any of these software packages into OptiSystem or Optiwave software into your machine at the program files folder on C drive. Next is let me see what's happening here. Okay. Here is just to show you some resources which you can use. One of them is Optiwave high definition channel on YouTube. There is lots of videos for using the software, and the webinars listed there. So it's a very good resources to look at the different products and different technical information which you can get. There is also on our website, there is a knowledge base page which you can get information about different papers or techniques or technologies and a demonstration of it. Quickly here, what I'm going to show you is about OptiSystem software, which is mainly used for characterizing the Photonic Integrated Circuit. We have over 610 components in the different applications can be used. Like we have a wide variety of light sources, including analytical models and measured models for lasers. Like you have CW lasers, LEDs, VCSELs, DFBs, and Fabry-Piro lasers, as well as white light sources. There is lots of optical modulators with Mach-Zehnder modulator analytical models, or you can have other types of modulators with single drive or dual drive, single port or dual port, as well as electro-absorption modulators. There is sources which you can load pseudo-random bit sequences or user-defined bit sequences which you can load using, let's say, for example, coming from an equipment. You can load that file into OptiSystem and then use it in your simulation. There is test compliance matrix, compliance patterns which you use for jitter analysis. Optical fiber, we have different types of fibers, single mode, multi-mode, as well as multi-core fibers, which can be used as a single mode, multi-core, or multi-mode, multi-core fibers. Electrical modulators, we support orthogonal frequency division multiplexing, as well as quadruple modulators for intermediate frequency generation. Modulation formats, we support all types of formats in the market, from standard on-off keying, which is like return to zero or not return to zero, or other advanced modulation like QAM or differential PSK or PAM, and so on. Filters, we support analog filters, digital filters in the optical domain and electrical domain, as well as fiber Bragg grating filters. Electro-optics circuits, there is different types of circuits can be designed in collaboration with OptiSpice software. So you can have laser drivers as well as designs for ring resonators and optical interconnects. There is signal processing. We have a sophisticated DSP component, which has lots of models to be able to do different compensation in your system. There is different types of regeneration, single R or dual R or 3R generators. bit mapping and forward error correction. We support with Solomon codes, forward error correction, or low density parity check. There is different type of mapping which you can be used for coding applications. Detectors, we have bin detectors, APDs, SPD, single photon detectors, or photon number resolving detectors. There is a wide range of dope fiber materials like erbium, ytterbium, thorium, praseodymium, holmium, as well as GaN blocks, which can be designed using semiconductor amplifiers or Raman amplifiers, as well as waveguide amplifiers. Electrical amplifiers, we support transimpedance amplifiers, linear regime or nonlinear regime, as well as automatic gain control and limiting amplifiers. Passive modules, any components you could think of it is available in OptiSystem, from couplers, muxes, array waveguides. So all of these models is analytical models. Some of them you can load your own measurements and use them in the circuit. Multi-mode applications, we support multi-mode fiber as well as multi-mode erbium amplifiers and multi-mode ytterbium amplifiers. There is mode generator components as well as spatial visualizers. Channels, we talked about fibers. There is free space optic channel, which can use it for visible light communication or Li-Fi satellite communication, as well as underwater wireless channel. Visualizers or equipment. So we have components or visualizer, which is mimicking the instruments in the field of optical instruments or electrical, binary, memory, as well as test equipments, which is used for like light wave analysis or filter analysis and so on. These components can work in the unidirectional or bidirectional, so you can do transmission in the east to west or west to east, as well as this supporting single polarization and dual polarization. And this slide shows you the interworking between Optiwave software. So OptiSystem can work with OptiGrating, with OptiBBM, OptiSpice, as well as OptiMode and FDDT, and OptiInstrument. So you can generate information or data from this software and launch it into OptiSystem and use it in OptiSystem. Also, OptiSystem can work with external software like MATLAB, Python, C++, Scilab. So you can do call OptiSystem from this software. So you can use your own code in Python or MATLAB, or and then you call OptiSystem to do some functionality and then get the data from OptiSystem and continue in MATLAB or Python. Or you can do the opposite. You can write your own code for a component or for some system. You have a proprietary information on it, and then add it up as a component in OptiSystem. So you run OptiSystem, and then when it reaches that MATLAB component or Python component, it calls the software and then do the calculation in the software and then get the results and then continue in OptiSystem. So either way can work. And finally, this Luceda component, which we talk about it today, mainly for testing the Photonic Integrated Circuit, which we're gonna concentrate on it in a few minutes. Now, OptiSystem software, as I mentioned, whereas we have over 610 components and lots of visualizers. And the other part of OptiSystem is the example library. We have over 1,000 examples, and these examples are categorized in different categories depending on the application. So we support applications for advanced modulation, for radio, front haul, for optical amplifiers and optimization, for microwave photonics, sensors, different types of PHY, OTDR, OTR, photonic crystal fiber for biosensing, optical wireless, which you support different type of channel, Li-Fi, visible light communications, and so on. Spatial demultiplexing, as I mentioned, you can do few modes or modes, multi-mode fiber, or you have single mode or multi-mode, multi-core fiber transmission, as well as quantum key distribution. We can have some examples, and there is example on digital image processing, and finally about the big system characterization, which we're going to talk about it with Luceda component. Now, as Nirav was saying about IPKISS creation of this Photonic Integrated Circuit, and then how we can take this design of the Photonic Integrated Circuit into OptiSystem and try to do a system level characterization. So we have this component called OptiLuceda, and then this component, you can run it in the time domain or frequency domain. And once you set up your domain of calculation, you either you have to have IPKISS software on your machine, so you can either enable a path for that software. So you can, if you say here user-defined executable location, if you don't, we detect that location automatically in by OptiSystem. But once you do that, what you need to do is you need to load the Python file for this photonic integrated circuit. This is done by Optiwave, basically this field. And then once you run, you click on this icon here, run. What's happened is this Luceda co-simulation component creates the ports. So in the file here, you define the location of the ports, the type of the signal, it is optical signal or electrical signal, where is this ports, you need at the top, at the bottom, and so on. Now, the icon in this part here, it defines the information about the port, but the last thing is the delete. So if you click on this button here, it deletes the ports and the component becomes empty. So let me go into my virtual machine here just quickly to show you the component. So the component in the component library, this is the OptiSystem GUI. And the example library here under the Optiwave software here, you have this component, which is Luceda. This component, if you want to build your system, is just as I show you here, you just drag it into the layout and then you build the component. As you can see here is the different fields. This is the domain, time, or frequency. And then here you load your signal and so on. Now, in this example, which we need to demonstrate to you just quickly, here, I'm gonna show you what is this button here, shows the information. If you click on it, okay, here, okay. Okay, so this button here, you have information about every port. This is coming from the Python file, which is created by Optiwave. You can enable editing, so if you want to edit the information here, you can do it, but else is gonna be exposed to the user, tell you every port, what types of the port, and so on. Now, once it's done this process, it goes into building the system around the component. So typically, each port here, as I mentioned, it has either optical or electrical. In OptiSystem, we have color code for each port. So if it is green, it means optical. If it is blue, it means electrical. And if it is red, it is binary, and so on. So you can pick up your components from the component library here and then build your system around it. The process is very simple. As you can see here, if you start with a layout, which is empty, you just go, for example, I need to take a laser. You go to sources. You have different types of lasers I mentioned. Some of them analytical model, which is the simplest model, or some of them has measured data. You can do here, as you can see, CW laser measured and so on. Now, around this component, you can build your, let's say, for example, pseudo-random bit sequence generator or user-defined. You can take the pulse shaping here, for example, electrical. You take the non-return to zero pulses, let's say, for example, and then you put your modulator around it, so you can have different types of these modulators. As I mentioned, this is the simplest model, which is analytical. And now your signal here, you generate an optical signal at this laser wavelength. If you double-click on any component, you can access the parameters of this component. You can set up the parameters, power, laser, and so on. So there is a lot of resources in OptiSystem. As you can see here, very simple and easy way to do building your project around the big component. Now, this project here, as you can see, we have 4 boards, and let me go back again to the slide to, no, not here, so go here. To continue, just to show you the discussion. So this is the block diagram, which we just saw in OptiSystem, show you the component here. You have data generated at each board of the switch. So you have 4 boards here, as shown by Nirav. There is 2 inputs here, 2 inputs here, and then each waveguide in here, we have a heater, which applied a voltage into it. And then at the output, you have 2 outputs here and 2 outputs here on the other section. And then you, by controlling the voltages, you can switch the input port into which whatever output port here, and that's where is the cross connection happening in the switch. Now, the voltages here, provider of the design will give you a truth table, and this truth table basically have the voltages applied to every heater here. As you can see, we have 6 digits here, and this every digit here is high voltage or low voltage. So low voltage is 2.416 volts, or high voltage 3.416 volt, and depends on the combination of this voltages applied. Like for example, if you take an example here, 010101, it means port 1 goes to port 4, and port 2 goes to port 2, port 3 goes to port 3, and port 4 goes to port 1. So it's this kind of configuration. It makes the connection between port 1, pass it to cross connect to port 4, and port 4 to port 1, however, keeping the bar between port 2 and port 3. So if you go now into OptiSystem, what we do in OptiSystem, a feature which is called let me go to the layout here again. If you double click anywhere on the layout on the canvas here, you can add up parameters. You can automate your setup here and do some kind of quick analysis for the switch. So for example, what we did here, we define low voltage, which is 2.416, a high voltage is 3.416, and then applied voltage here, V1, V6, which is the 6 voltages on each electrode. And then what you can do here, functionality, we call it sweep. So what you can do sweep on these voltages. And once the setup of the sweeps, we can do some kind of automation here. So if every sweep, we can have certain configuration, which is the switch status. Here we took an example, only 5 of the truth table, just only to demonstrate. But eventually you can have all of this truth table and then run them at single run, okay? And then would give you all the analysis. So once you accept the settings, and then you run the project. I did run the project ahead of time just to save time here. But once you run the project, what you can see, you can analyze the result of the switch. For example, in this configuration, we have 5 iterations, as I showed you. This iteration is the one which I selected in the switch, which is low, high, low, high, low, high, which means port 1, which is coming here, it's supposed to go to port 4, and port 2 to port 2, and port 3, port 3, and port 4 to port 1. So now in the OptiSystem example library, OptiSystem visualizer library, here you have the different equipment. There is a single port equipment, or there's compare, which is dual port equipment. So here, as you can see, this is dual port visualizer for pulses in the time domain. So if you look at the pulses coming on port 1 and the pulses which is coming at port 4, you can double click here, and then you can do your analysis on the signal. So you can zoom, for example, on these pulses. As you can see, this is the input, this is the output, there is the insertion losses. You have markers in here. You can set up your markers and read your, for example, time domain, how much is the delay to the switch would incorporate into your signal. You can look at the insertion losses and so on. You can have spectrum analyzer, and then you look at the spectrum. You can control your resolution and so on. And then eventually, at this situation right now, we're analyzing the cross connect as back-to-back. It's just only transmit and receive. The bend detector here, you can incorporate into it different type of noises, shot noise, thermal noise, beat noise, and so on. And you can control every parameters. You can control the bandwidth of the detector. And there is different types of detectors. You can have ABDs, single photon detector, and so on. Depends on your application. And then here you have a filter. This is analog filter, a low pass filter, and then the eye diagram analysis. So you can have different types of analysis. You can look at the here eye diagram, and you can look at the Q factor, BER. If you right-click on this visualizer, you can have results, lots of results available for the user to look at it and analyze. There is a report page here. You can create graphs, 2D, 3D graphs, and so on. So it's lots of flexibility in terms of the project and so on. So in simple terms here, you can build if you want to see the switch, how it's going to be in a channel, you can go to optical fiber. You can add up fiber channel. You can go to the free space optic channel, and then you can add up either a free space or Li-Fi or satellite or underwater. So it's lots of flexibility. You can add up into the system. You can do any type of modulation in the system. The example library is here, so you can go to the example libraries, which is going to show you all the examples available for to build on it and learn from it. Okay, so let me go back again here into the characteristics. Okay, so again, if you double click here, you go to the setup. You can add up parameters, you can automate, and you can run sweeps here. And then the thing is also one thing which you need to pay attention in it is the characteristic which Nirav showed in the analysis. One important part to system analysis is to know how much is the filter can work. In communication system, you have a limit on the crosstalk between the channels, so you can set up your limit, and then you can see if you need to do more than one wavelength. In the example we built here, if you go again into the example, all these channels are running at the same wavelength. If you need to run at different wavelengths, you need to know what is the bandwidth of this filter and what is your tolerance on crosstalk. Okay, so and then you be able to use different wavelengths on your cross-connect switch. Okay, now here is again the delay analysis, which I showed you, the eye diagram analysis. And with this, I conclude and open to questions. But if you want to download our free trials, please go to our website and download. If you have any question, please don't hesitate to send me email or send an email to support. Thanks very much, everyone.
Okay, thank you very much for both of those very interesting talks. So now we will open up the floor to some questions. I believe there is already a question in the chat. If I can just access the... why is this...
Greg, the question is in chat.
Yes.
Is the layout to schematic transition enabled via Python script in IPKISS?
So yeah, I can answer that. Yes, indeed. So it's just one line of Python code you have to write, and it will export whatever circuit you draw in IPKISS to our GUI tool, which is Canvas. Does that answer your question?
I think the question is by Ratisha.
Welcome.
Okay. And any other questions from the audience? So if you do have a question, please unmute yourself and ask. Okay, maybe I have a question, just a sort of a general question, really. So what are the next steps then for this integration between these two tools?
Can I answer this?
Sure.
So the link is fully functional today, but of course we want to get this link in the hands of customers to see how they use it and get feedback from them. So if you'd like to use this link, please get in touch with us and we'll discuss the next steps.
Yeah, let me add up here, elaborate a little bit more also, Craig. So I think this integration between the Luceda and OptiSystem is very useful for the designers to be able to, before manufacturing of their devices, to be able to manipulate the design and then try to see its performance and put some kind of specifications on the device when they manufacture it. So this is one thing which could be very useful for any PIC designer, is to use this integration for actually identifying the performance of the devices in the system level, which is not only in the PIC as a device, as a PIC device is enough to be able to say that this device is going to be working efficiently in a full system. So this integration is a tool to allow the kind of the full device characterization, which is I think is very important for system designers eventually when you want to build your photonic integrated circuits, to know that. So the integration is very important from that perspective.
Okay, great. Thank you. Are there any other questions from the audience? Okay. So I'll just add something just as we're coming to near the end of the time. So we've seen a lot of information today from both Luceda and Optiwave, and as mentioned in the slides, it's well worth checking out both Luceda and Optiwave's websites. You can see here we've provided some links in this slide where you can discover more about Luceda, and you can discover the Luceda Academy and the application examples, and you can also explore upcoming events that we have. And similarly, you can see the links for Optiwave and OptiSystem, and as Ahmad shared in his slides, there are many links there to the knowledge base and all of the interesting application examples they provide. So please be sure to check those out. If you have any specific questions that come up after, or you think of after the event, please don't hesitate to reach out to us. You can find the contact information on both of our websites, and you can ask away, and we will gladly answer any questions you have. Okay.
I'm not sure, Craig, if we can advertise that we will be at OFC, and if anyone interested, we can meet there as well.
Sure. Yes, we will both be at OFC. So if any of you are attending, yes, please reach out, and we will gladly receive you at the event.
Yes.
Okay.
Perfect.
So if there are no more questions, I think we can end the session here. And again, I'd like to thank both of our speakers for their presentations today, and to thank everyone for joining the session.
Thank you. Thank you, everyone.
Thank you.
Bye.
Okay, thank you.